Yes, friends. So good evening, everyone, once again. And after a 2 or 3 days gap, we are meeting once again. Okay. So in this 2 3 days gap, friends, actually, I was not able to look at your comments because around 68 comments have crept in past 2 days since I think since Saturday night I haven't taken any class. Okay. So since Saturday night, 68 comments have crept in my account on my YouTube channel, and these 68 comments I literally did not get any time to look at those 68 comments. Okay, and now the number has even rose up. It has rose up to 72 now. Okay, so it is really impossible to look at your comments and check each and every comment. So don't worry, although I would not be able to look at your 72 comments, but I can assure you one thing, that you may contact me on WhatsApp in case of any doubt. Okay, so in case of any doubt, you have my WhatsApp number, which is 7249187038. Okay, so you can surely contact me on my WhatsApp number in case of any serious doubt, if you have in case. Okay, so you can surely contact me on WhatsApp regarding that. But one thing, and regarding doubt solving support also, the response was good. Almost 3 students have already joined the doubt solving support. Okay, and one student is going to join, Kamrup Mandal. I think he is going to join the doubt solving support. Okay, so if someone of you wants to join, so he or she may go for it also. Okay, now friends, we will move on towards our next topic, which is Dirac notation. But the thing is, friends, I am teaching on tablet right now. Why I am teaching on tablet? Because my laptop has crashed. Okay, my laptop has crashed, and one more thing is there, that I was ill since 2 days, and I did not get any time to look at the laptop. Okay, and that's the reason why the class was not there, and also laptop has also not been repaired yet. So that's why we are studying right like this now on tablet. Okay, so let's see this Dirac notation. Regarding that, we are seeing. So what does this Dirac notation actually mean? We are going to learn it. Dirac notation means the same thing as your Bra and Ket vectors, which Bra and Ket notations, which you might have learnt in your lower classes, right? So that's the very same Bra and Ket, not in lower classes. I mean, by lower classes, I mean in BSc you might have learnt Bra and Ket vectors. Okay, Bra and Ket algebra, and in MSc physics it is in detail, right? So the same thing we are going to learn now, but before that we need some introduction type thing. Okay, so the same introduction is going on right now. So wave function defines a state of a particle. Okay, we have already discussed this. Wave function, what does it do? It defines the state of a particle. Okay, so let capital F be a set of all possible wave functions of a particle. It is known as basically state space. You know this very well, that there are all possible wave functions may be there. For example, psi1 is suppose a possible wave function for a particle. So similarly, psi2 is also possible wave function for a particle. Psi3 is also possible wave function for a particle, suppose I am saying. Okay, then what does happen? Okay, what happens is, suppose this is for first energy state of atom, suppose this is for second energy state of atom, and suppose this is for third energy state of atom. So for different conditions we have different type of wave functions for a single particle, that is electron. If it is subjected to different conditions, we have different type of wave functions. Okay, so each of these possible wave functions is known as state space. Got it? It is known as state space. So the same thing has been written. Okay, so many properties of F. Okay, many properties of capital F, that is your state space. Many properties of F, that is your state space, are identical to set of geometrical vectors. You might have learnt the algebra of geometrical vectors in 11th and 12th, and also now you must know it in order to crack UPSC with physics as an optional. So you have learnt the vector addition, like the sum of two vectors is equal to a third vector, linear vector, right? You have learnt the scalar product of vectors. So scalar product of two vectors yields a scalar, right? And you have also learnt the vector product of two vectors, which is again a vector quantity. But over here, while we discuss the space, while we discuss the vector space, wave function space over here, state space over here, wave function state space, while we discuss that over here, we simply mean that cross product is usually not defined. Okay, you must remember this thing, that for state space, the state space which consists of many wave functions, all the possible wave functions, okay, usually cross product is not defined. Okay, usually I am saying, usually cross product is not defined. Okay, cross product means it is not called as cross product, it is called as vector product actually, but that vector product is actually not defined in case of state space. And scalar product is defined. Okay, scalar product is always defined. Scalar product is always defined. Now never call it dot product, as in the world of state space we call it scalar product only. In case of normal vectors which you have learnt in your lower classes, which are the geometrical vectors, geometrical linear vectors, in that case only you can say whether it is dot product or cross product. But over here, when we talk about state space, you will always use the word scalar product and vector product instead of dot product and cross product. You should not use dot product and cross product words. Okay, so many properties of this capital F are identical to set of geometrical vectors. I already told you, right? And F is an example of linear vector space, right? Linear vector space. Why linear? Because clearly why it is called as linear? Because it satisfies the relation, right? A plus b, a vector plus b vector is equal to c vector. It is satisfying that relation. And why it is called as linear? Because it satisfies the property of linearity. You might have learnt that the like this, suppose if I multiply a constant to this linear vector space, then constant multiplied, this distributivity law holds good in case of vectors, right? So in case of vectors, as this distributivity law holds good, so they are called as linear. You might have learnt about linear integration, also linear functions also in your lower classes, right? So you have also learned this thing that d by dx of u plus v is equal to du by dx plus dv by dx, right? So why is differentiation a linear function? Because when I take d by dx of u plus v, I get du by dx plus dv by dx, right? So it can be law of distributivity holds good over here, right? So that's why it is called as linear function. Differential is called as linear function. So similarly, this is an example of linear vector space, and the various wave functions which are associated with this vector space are called as state vectors. Okay, they are called as state vectors. Got it? Now what did direct do? We are going to look at that. To denote a state vector, direct did one thing. that Dirac introduced the ket symbol, okay, to denote a state vector. Okay, so this is the ket symbol, and it simply means that you will have to put psi inside this. Okay, now in real life, if we write it without even putting psi as an argument over here, okay, even then the things will work for us. Suppose if I put psi as an argument over here inside this ket symbol, okay, so if someone wants and he is at advanced level in quantum mechanics, then he might write it without the psi symbol also, just as a ket notation. Okay. But for our convenience, we are always going to write the argument psi inside this ket symbol. But what does this ket symbol mean? Ket symbol simply denotes the, for example, the psi denotes your wave function, right? Psi denotes your wave function. So when I take its ket, okay, when I take its ket, I simply mean to say that it is a space. Okay, it is a space. It is a space of all such state vectors. Okay, it is simply a space of all such state vectors. For example, there will be various values of psi. All the possible values of psi will be taken, and it will be a space of that. So such a space is denoted by the ket symbol. Okay, now when we take its conjugate, okay, what happens? When we take its conjugate, simply we denote it by star. Okay, conjugate is denoted by star, right? So when I take its conjugate star, so it is denoted by bra. Okay, so conjugate psi star is denoted by bra, and it is just of opposite notation. Okay, your ket symbol is like this, but your bra symbol will be exactly opposite of this. Okay, I mean opposite means I mean mirror image of this. Okay, by opposite I mean it with the symbol of bra will be mirror image of the symbol of ket. Okay, so the conjugate psi star is denoted by bra and scalar product by bracket. Okay, how is a scalar product represented? It is represented by bracket. Okay, so now you can look over here that psi is like this. Okay, psi star is like this, right? And suppose if we take the scalar product of two wave functions, phi and psi, suppose in case, okay, suppose in case if we take scalar product of two wave functions, psi and phi, okay, so clearly over here we might have a look at one thing, that this symbol, it is bra phi. Okay, from here if we take the analogy, then clearly it is bra phi. This symbol is what is this symbol equal to? This symbol I am saying. Okay, so this symbol is clearly equal to bra phi. Okay, bra phi. And what is this symbol equal to? The next one. Okay, the next one, this symbol, it is equal to basically your ket psi. Okay, this was bra phi and this is ket psi, right? So clearly we can expand this scalar product. Never call it dot product, although it is very similar to dot product. It has a clear analogy with dot product, but never use the word dot product over here. Okay, this scalar product is basically called as bracket. Why it is called as bracket? Because over here bra is also present, right? Over here bra is present, and over here ket is also present, right? Over here ket is also present. So that's why the scalar product is being called as bracket, right? So clearly you got this. Now let's have a look at this, that how it actually looks like. Okay, how it actually looks like. So clearly you might have a look at this, that when we define it, it looks something like this. I already told you that the bra symbol denotes conjugate, right? Complex conjugate. Okay, so complex conjugate of phi will be 5 star, and there is no complex conjugate of psi because it is under ket symbol. So if you have a look over here, this is under bra symbol and this is under ket symbol, right? This is very, very clear from the figure. So the one which is under the bra symbol, that shall be opened with the help of what? Which is under the bra symbol will be opened with conjugate. Okay, so 5 star will come, and whatever is there under ket symbol, that will open normally, right? So as it is a 3-dimensional space, so d tau has come over here. If it would have been a 1-dimensional space, then dx would have come over here. Okay, over here it is d tau, but if it is 1-dimensional space, then dx will come, right? You must have seen the previous lectures, and from there you might have an idea about that already. Okay, so now to every ket, okay, to every ket there exists a bra. Okay, and this is very, very important property, that to every ket there exists a bra, such that when we take the complex conjugate of that ket notation, like the one given over here, when we take the complex conjugate of that ket notation, we basically get the bra symbol. Okay, we get the bra notation. Okay, so after I took the complex conjugate of this, I got basically the bra notation. Okay, so complex conjugate of ket notation is basically your bra notation. Okay, now if there is also a constant multiplied over here along with this ket notation, then obviously the complex conjugate of this will go over this also and over this also, so it will become a star bra psi. Okay, so a ket psi is complex conjugate of a ket psi is equal to a complex conjugate of a, means a conjugate bra psi. Okay, when a is complex. Okay, so this is quite evident from here. Okay, when a is complex. Okay, now a is obviously a complex number, because if it will be a real number, then it will not be written as a star, it will be written as simply a. Okay, now it may also be a real number. Okay, so yeah, over here there is one slight mistake, where a is a complex or real number. You might write it like this. Okay, where a is complex or real number, because in case if it is real number, then this a and a star will be the same, it will become a only. Okay, so in case of real number, over here a will come. Okay, rest all of the things will remain the same, because the complex conjugate of a real number is the same number, right? There is no difference between the complex conjugate of a real number. So this is a real number, its complex conjugate is going to be the same. Okay, a star only, right? Complex conjugate will be the same. Now complex conjugate of a real number will not be denoted by a star, that's all I mean. Okay, it will be denoted by simply a. It is over here, it must be a complex number, so that it is being denoted by a star. Okay, that's what I meant. So in one dimension, this is very clear, that from the definition which we saw earlier, from there it is very clear that this part is bra, and this part is, what is this? The first half of this symbol. Okay, what is there in the first half? Over the first half of this symbol, it is bra psi 1. Okay, so as it is bra psi 1, so complex conjugate of psi 1 will be taken. Okay, and in the next half it is ket psi 2, right? Ket psi 2. So as it is ket psi 2, so without complex conjugate means the same function will be taken. Okay, so ket psi 2, so the same function has been taken over here, and bra psi 1, so complex conjugate has been taken over here. Okay, so in one dimension it is written like this, minus infinity to infinity. Okay, now dx is there, so it will be clearly one dimension. Okay, dx is there, so it will be clearly one dimensional case, right? So a number that may be complex. So what will come over here? The integration of this will be equal to a number that might be complex number. Okay, the integration of this, if you take the integration of this, it might come out to be a number that may be complex. Okay, and yet that may be real also. Okay, not necessarily a complex, that might be complex or might be real. Okay, you might write over here, or might be real also. Okay, might be complex or might be real. Okay, so it's not necessary that it will always be complex. Some people are confused over here. Okay, so it's not always complex number, but this integration may also yield you a real value too. Okay, sometimes it might yield you a real value, and sometimes it might yield you a complex value. Okay, so clearly from here it is very clear that these two will be the complex conjugate of each other. Now you must also only tell me that why will these two be equal, because you have basically interchanged the psi 1 psi 2 symbol, right? You have made the ket of ket bra here and bra ket over here. Okay, so you have basically interchanged the symbols, and if you interchange the symbol, then when you take the complex conjugate of it, the same result will be obtained. So you took the complex conjugate over here, so that the value remains the same, equality sign holds. Okay, in order to equality sign hold good, you have basically put the star over here. Okay, why have you put star over there? Because you have interchanged the wave functions. Okay, or you might call them variable also. Okay, so you have changed the arguments, you have interchanged the arguments, you have made the ket as bra and bra as ket. So after you interchange those, you will have to put the complex conjugate symbol on the other one. You have to put the complex conjugate symbol on the other one, so that their equality holds. Okay, so in order to equality hold good, it is done like this. Okay, so only if scalar product is real number, then now you only tell me that if this star and all these things will mean good, this star and all these things will mean good in case of complex number, right? But in case of real number, you know this very well. In case of real number, you know this very well, that the complex conjugate is same as the real number itself, right? So in case if this value comes out to be real, okay, if suppose these values come out to be real, so what will happen? Even if I take its complex conjugate, which is written over here, okay, even if I take its complex conjugate, suppose real value is coming. Okay, suppose real value has come, and even if I take its complex conjugate, the value is going to be the same. So only if the scalar product, this is what is the scalar product. So only if the scalar product is real number, okay, only if it is real number, then we will have psi 1 psi 2 equal to psi 2 psi 1. Okay, but when? Only if the scalar product is real number. Okay, because in case of a real number, the star symbol, which is the conjugate symbol, will no longer be a meaningful symbol. Okay, because the complex conjugate of a real number is the same real number itself, because it has no iota term in it. I have already told you all this in the preceding classes. I don't think there is any need to repeat this further. Okay, so thank you very much. Jai Hind, Jai Bharat. Up to here only we will study now. Okay, so thank you very much.